All right, so today we're going to do two compound circuits, a little more complicated than we did last time, and I'm going to run through the first one here that has 8 resistors in it, and then your job will be to analyze the second circuit that I believe has 11 resistors in it. Okay, so remember, the first thing you want to do is you want to redraw the circuit as though it were in a line. So you want to take it from a loop and just stretch it out into a line. And you want to take note of all these little junction points, and that's the little red circles with numbers in them. That helps you to keep track of where the wires actually unconnect, split, and reconnect with each other. So let me draw this out in a line, and you'll notice it comes off the 24-volt source and goes through resistor 1, and then it gets to junction 1, and it splits off where you have a choice to go to junction 2, where it splits into 2 resistors in parallel, and the wires reconnect at junction 3. Then they split again at 4, where the electricity can go through either resistor 4 or 5, and it reconnects at 5, goes down, and you'll notice here in the original drawing, it turns a corner, then turns a corner again, but in our linear drawing, it just goes straight to junction 6, where it splits to 2 parallel 4-ohm resistors, rejoins at 7, and then rejoins the original split off at junction 1 for that 3-ohm resistor, and then on into the end of the battery. All right, so now that we've got it drawn out in a straight line, it's time to start combining resistors that can be combined. So here we can certainly combine resistors 2 and 3, resistors 4 and 5, and resistors 6 and 7, because those 3 pairs are just 2 parallel resistors together. And you do that by using the parallel reciprocal series equation, which means for resistors 2 and 3, you would add 1/4 plus 1/1, and then take the reciprocal of that, and you get a point. They're equal to a single 0.ohm resistor series. For resistors 4 and 5, it's 1/1 plus 1/3. Then you take the reciprocal of that and get a 0.75 ohm resistor. For resistors 6 and 7, 1/4 plus 1/4 is 1/2. The reciprocal of that is a 2-ohm resistor. And you couldn't yet have done anything to resistor 1 or resistor 8. Okay? But if you look here, these 3 resistors on top are all in series with one another, so we can take care of those by using the series rule and just adding them up. So 0.8 plus 0.75 plus 2 is 3.55 ohm resistor. And now we still can't do anything with resistor 1, but this conglomeration of resistors 2 through 7 and resistor 8 are in parallel with each other, so we can redraw them as though they were just one resistor. 1/3.55 plus 1/3, and you take the reciprocal of that, and you get 1.63 ohms. Now we have 2 resistors in series that we can simply add up to a total 3.63 ohm resistor. And so now we know that it's 24 volts, a total of 3.63 ohms of resistance, and we can solve for the current by doing the 24 volts divided by 3.63 ohms of resistance and get 6.6 amps of current through the system. And now now that we know the total voltage, resistance, and current, we can start going back up through our drawings and finding the voltage and current at each one of those resistors. And here, this one resistor that was a compound of all 8 resistors was actually 2 in series. So what we do is we take that current, because current is the same in a series everywhere in a series circuit, and then we can solve for the voltage. Voltage is current times resistance. And then it looks like we're done with resistor 1. We have the voltage, the current, and the resistance, and that is back to the original resistor. But for this combined resistor 2 through 8, it was actually these 2 in parallel. So we'll take the voltage of 10.8 and apply it to both of those two resistors. Then we can solve for current, because current is voltage over resistance. And that means resistor 8 is now done. We've got the voltage, the current, and resistance for 8, but this combination of resistors 2 through 7 was actually 3 resistors in series. So we can take the current of 3.1 amps and apply it to all 3 of these in series, and then we can solve for voltage. Oops, sorry. Okay, voltage is current times resistance. And then we can take, since like here, this combined resistor 2, 3 was actually 2 in parallel, and this combined resistor 4 and 5 was 2 in parallel, and this resistor 6 through 7 was actually 2 in parallel. We can take the voltage from each one of these resistors and apply it to the 3 pairs of parallel resistors and solve for current. All right, so I know that was kind of quick, but remember, you redraw, you crush parallels down and combine series down till you get to one equivalent resistance. You use the voltage to find the total current, and then you carry current up to series and solve for voltage. You carry voltage up to parallel and solve for current, all the way until you get back to the top and get to every individual resistor. Now it's your job to move on to the second one and try to solve that. It's a slightly more complicated, but I want you to give it a shot. Okay, and it looks like this. And one thing I'll do here in a second is I'll put up the first drawing, because you have to get that original drawing correct so that you can start to compact series and parallel resistors together. So go ahead and make the drawing yourself and see how well you do. But this is a way to draw it out as a line, and yours doesn't have to look exactly like mine, but it should have basically the same junctions, and certainly should have these 3 resistors 1, 2, and 3 in series, and those 3 in parallel with resistor 4, and then resistor 5 in between the 2 sets of parallels. The second set of parallels would have 6 and 7 in series, and 8, 9, and 10 in series, and then to the end resistor 11 is off by itself. And now start to solve. I don't know how many drawing it's going to take you, 5 or 6, but give it a shot, and I will put the key up later. Thank you.